So I see we have about 15 minutes left. We're not going to go through all of this part. So we're mostly going to look at the types of trends. Maybe we'll look at assessing trends, but we'll save definitely the rest of this, removing trends, decomposition, as well as modeling for next time, just kind of being aware. Okay. So looking at trends in general. So I'm just kind of showing you some data quickly from before. So we can import our library or import our libraries. We can get our New York Stock Exchange data. Note that I'm converting this over to date time, right? I'm not doing any resampling or anything like that. And then in this case right here, you can see that I'm actually generating some data. So I think this is actually from the curriculum, if I remember this right. But basically we have our years here, basically just making up data, a period of 72, our frequency is monthly, right? Our date time index is years, right? So I'm making sure we actually have a date time, random information. And then if we actually do this, we can see a little bit. Oh, sorry, I realized I didn't pull this out yet. We'll use this in a second, but basically I'm making some time series data essentially from these data points. And then I'm taking this part right here, basically just making some random data. Okay, so this will be important when we see different trends. All right, so our different trends are going to be focused on stationary, linear, exponential, and periodic. So stationary, I like to think is like the most basic, like what we want. Like if we can decompose, if we can take any trend and break it into different parts and look at just a stationary, basically stationary means it's not moving, okay? So there's a great article that I think the curriculum actually points to, basically time series modeling, but you can think of stationary as a no trend. So looking at the New York Stock Exchange right here and going forward, okay, you can see basically there isn't a clear trend here. You might call this stationary. So our goal is kind of to check like, hey, does this data set, does this trend, this time series actually have no trend? And that would be something we call stationary, okay? Now, we'll later look at something called decomposition to actually build out the different parts. So there might be some little patterns in here. Like for example, you can say, well, there looks like there might be some kind of pattern in here. It's not completely stationary. So our goal basically will break it down to a stationary trend. So we can check that out, okay? So not really super interesting. So the next part is a linear trend. And as you probably guess, a linear trend looks just like a line going up. So you can see here is that a linear trend in this case. In this case, it looks like UK imports and just increasing over a year, right? So that's an upward trend, and a downward trend would look very similar, but downward, okay? So you can see a little more interesting than no trend, right? But also pretty basic, right? Now an exponential trend, to be quite honest, you probably will see this quite often. So an exponential trend, note that looks like the linear trend at first. So you can see here, like if I look at this from 2012 to 2015, and I'm going to draw a little bit on here. Let's get me red here. So you can see here going from this point, you can kind of see it's more or less a line, right? But the important part of the exponential trend is that it increase more and more, or increase faster and faster over time. So you can see here is that this is when it basically breaks that linear trend and we're actually increasing over and over. So an exponential trend basically follows an exponential curve, right? Something to the power of something, right? So you can see here it's going up and up and up and up faster. But I think it's a really important aspect to note for exponential trends is that a lot of times they look like linear trends until you go far enough into the future, right? And then you see, okay, that's when the exponential trend really takes off, okay? And that's basically like an exponential trend might be rated something like e to the power of x, right? It could be any number, but that's usually how you see exponential trend. This is about equal to x when the numbers are very, very small. So if you actually put this in your calculator, if you put something like x to like 0.01, this is about equal to 0.01. So that's essentially why you see an exponential trend at the very beginning look like a linear trend, because this right here is what a linear trend is. Okay, does that make sense to everyone? Okay, cool. So that's the next big one. And then periodic trend, as you probably can guess, is when we have something changing over a period, right? So periodic, you can see here, oops, there we go. You can see here a couple periodic trends right here. This one right here definitely has some like fuzziness going forward, but you can definitely see something kind of periodically going through, and you can probably see it's like, oh, temperature and the date. You can probably guess this is probably because of winter and summer, right? We can see a periodic trend here as well. This one is actually, these are all from the curriculum, by the way, but this one in particular was the one I had mentioned about flights and stuff like this from the curriculum that you can go through. And basically you can see here is that there definitely is a trend on like a number of miles flown. I think that's what this data set was about. So number of miles flown per year. And you can see that there is definitely a periodic trend, right? Of saying, okay, maybe like during the holiday season, there's a lot more miles flown. But you can also see there's a general like upward trend too. If you kind of look closely at this, right, you can definitely see like the bottom part going up slightly. And so you can see there's actually a kind of a mixture of periodic and linear trends. So note that you might see these multiple trends in going for our time series data. And this is actually going to be into later on into decomposition. We're actually going to pull out those different trends from the different time series. So we can break it down into a periodic trend, or we call it seasonality. So we take out the seasonality, we take out the linear trend or exponential trend possibly, and then basically see like if what's left over is stationary. And if that leftover is stationary, it means that we accounted for all the aspects. But if that last part isn't stationary, it means that there's some other factor in there that we didn't account for that doesn't explain from the periodic trend or a linear trend or exponential trend. Okay, cool. So I think we have enough time for assessing trends. So we'll go into that, and then I think that's where we'll probably stop. And that will be good for removing trends and decomposition. Okay. So there's a few ways we can kind of assess these different trends. So just looking quickly at this data set, I kind of said like, oh, look, it's stationary. How do we know it's stationary, right? So you could say like, well, there doesn't seem to be a trend in there, but of course, as a data scientist, you probably know is that that's not a good enough answer, right? You can't just say, well, it looks stationary. And that's where we can actually kind of assess this and see if there are trends that in here. So one common way to do this first is something called rolling statistics. Has anyone heard of rolling statistics before? Or a rolling average or a moving average kind of thing? Okay, so rolling statistics basically, essentially what we'll do is we'll take a window and we'll move that window across to basically figure out if there is a trend within that window. So essentially what we'll usually do is like an average. So essentially if I imagine taking like a little, I'm just gonna draw it really quickly, is that if you imagine like taking like a little window right here, and essentially what we do, we average, it's like, okay, average these points to like one data point. Like this averages to this right here. Then we make a new window. Use, let's see here, use purple. Okay, so we can do something like a new window. So we move that window over a little bit. So there's a little crossover. And we average this point. It's like, oh, well, these average to like right here. And essentially we can keep doing these windows and moving this window and average those different data points. And that's what we mean by a rolling statistic. It basically rolls over, right? It's like kind of like rolling a little window across and taking the average as we roll that window over. And that can basically help us kind of smooth things out. So just to kind of see what this example looks like, you can see here is that I have a few parts in here. So this rolling mean, so our rolling mean and our rolling standard deviation, okay? It basically, take our time series, which remember I made up way before, this is all random data, and I take a window, basically I take 6 points. So I'm making a window of 6 points large, and I'm gonna move that window across, basically across the whole time series going forward. Actually, I'm wondering if I should have plotted this out. Let's plot. Here, I'm gonna just show you guys what this looks like. So you can see this is the time series, the TS data. So you can see here kind of going forward is that what we're gonna do is we're gonna move a little window that's gonna move across 6 points over. And I'm actually gonna make this 6 as well for standard deviation. I'll calculate the standard deviation for that moving forward for standard deviation. And basically this will help us be able to smooth out this part. And then the rest of this is just plotting each individual part together. And so you'll see here is that you can see here is the blue data, the actual data of what we've seen before. And this red right here is rolling that window across the data point. And so you can see here is that our data point only starts right here is because it has to average the first 6 points. So basically average those 6 points and says, oh, that average is right here. And then it moves it just off by 1. So it's a new window that goes like this. And that's a new data point, and basically keeps moving that window and making a new data point for each of those 6 points. And you can see here, it kind of smooths it out. If you can see, that's a much smoother aspect. And that kind of helps remove a lot of like the little fluctuations between, okay? On the black here, you can see the standard deviation. Basically, I'm just taking the standard deviation over time. So you can see, does the standard deviation change over those 6 windows? And you can see for the most part, it doesn't really change too much. Like maybe there's a slight change over as we get increased over here, but for the most part, the values don't change too drastically. What happens if I increase this window? What would we expect with our red line right here, our average? Would we expect that average to look more bumpy or more smooth if I increase our window?
Smooth.
Smooth. Okay, so thumbs up for smooth, thumbs down for bumpy. Okay, cool. I see a lot of thumbs up. So if I do this now, we should see a smoother one. If I do this, we can actually see it smooths out, right? And so why does it smooth out? Well, it smooths out because we're basically taking over a larger period, right? Essentially, we're averaging over longer points. Note that over here on the exponential part where it goes up significantly, it underperforms what the value is here. And the reason why is because these lower values are dragging it down. Remember, the mean is sensitive to outliers. So if there's a lower points down here, and it's exponentially going up much faster, well, that's going to drag it down, okay? And as you can probably guess, if I make the window smaller, it'd be bumpier, right? And then, of course, what if I did a window of 1? What would that look like? I'm going to guess.
That would just be the same line, right?
Same exact line. Good. Thank you, Thomas. You can see it matches exactly because it's a window of 1. It's taking one data point and averaging over just the same point. So good. Okay, and that's how you can imagine like changing that window. Sometimes the window makes sense in a moving average where you know like every 6 months or every 3 months or a quarter, something like that, you might do a moving average to help you envision how that smooths out. Okay, but the main point here is that it'll remove, you can see it remove some of that fluctuation that goes from point to point. Okay, cool. Any questions on these moving averages? All right, cool. So we might have just enough time just to talk about dickey-fueller tests. So a dickey-fueller test basically is saying, okay, if you have a data set, it's a hypothesis test, essentially say, is it stationary? So there's some more information right here from this link. I think it's also linked within the curriculum, but it's a good read. It basically says like, why does dickey-fueller work this way? But the main thing is I'm going to show right here, essentially I'm going to import it from stats models right here and know that basically I'm taking the dickey-fueller test, right? So AD Fuller, right? Is how we abbreviate it here. This is from the curriculum itself. And you can see here, basically, we're taking our we want to see our test statistic, our p-value, number of lags used, number of observations. And if I print this out now, you can actually see it's like, okay, these are our different values as you kind of see it from here. But it's probably easier to do a little printout right here, and you can see our test statistic. So this is, as we just talked about from module 3, we have essentially our what's it called? Our test statistic, like measuring our t-value, right? Our p-value, saying like, you know, is it significant or not, right? Number of lags used, and basically note that this is basically figuring out how many lags, how big of a window we're actually looking at, and how many observations there were, and basically saying, is it critical or not? In this case, a p-value of 1.0 is probably pretty high, right? You can probably guess is that this is not a stationary then. So there definitely is, as you probably can guess from just looking at this guy right here, this is not a stationary trend, right? So there's a high probability that this is not stationary. No, I could probably put in, let's see, New York Stock Exchange. Let's see if I can do that. I see, that's what I expected. There's too many values in this, I guess, so I can't pull it out. But if I had something that looks more closer to stationary, we can actually test this part out. And so we can actually use dickey-fueller to essentially, when we do decomposition, when we decompose and try to pull out, like, for example, this exponential trend, maybe there's some periodicity in here, like seasonality, we can pull those parts out, and what's left over, we say, okay, is that stationary? And if that part's stationary, then we know that we essentially have modeled that time series with what we have already. If there's more to do, then we can basically take that time series and go further into it and see if we can explain the rest of it. All right, so cool. So we'll leave these removing trends and time series decomposition to next time on Thursday, as well as we're going to talk about modeling with it, basically our different types of models, and then into ARIMA models. But any questions on anything we covered these this past hour? No? Sound pretty good? Okay. All right, so I'll go ahead and stop the recording here.